Welcome to The Explainer. So today we're unraveling the absolute backbone of the modern internet. It is the single, most critical routing protocol that holds the entire web together. I mean, it literally takes billions of chaotic, independent networks and weaves them into one cohesive system. We're of course talking about BGP, or the Border Gateway Protocol. If you've ever wondered how your data actually finds its way across the globe in milliseconds, well, you're in the exact right place.
Okay, let's dive right into this. How does the internet actually connect? I want you to zoom way out for a second, far past your home router, past your local neighborhood node. When we look at the global internet, it's a massive, almost incomprehensible scale of networks. For data to get from a server in Tokyo all the way to a smartphone in London, it doesn't just travel down one long wire. No way. It has to navigate this chaotic web of different providers, corporate networks, and global carriers. To make sense of all that chaos, we need a universal mapmaker. And that mapmaker? That's BGP.
Now, to really grasp how BGP pulls this off, we first need to define what an autonomous system, or AS, actually is. Think of an autonomous system like a giant, unified network that's completely under the control of a single administrative entity, like a major internet service provider or a massive tech company. Now, here is the absolutely crucial point. BGP was not built to route traffic within one of these autonomous systems. It's a path vector protocol designed specifically to route between different autonomous systems. Each AS gets assigned a 16-bit number, ranging anywhere from 1 to 65,535, just to uniquely identify it on the global stage.
So here's our roadmap for today. 1. The Internet's routing protocol. 2. IBGP versus eBGP peers. 3. Building BGP relationships. 4. The BGP synchronization rule. And finally, 5. Scaling BGP networks.
Section 1. The Internet's routing protocol. Exterior routing. Because BGP routes between distinct networks, it's what we call an exterior gateway protocol. This is pretty different from the interior protocols you might already know, like OSPF or EIGRP, which work purely inside a single network. BGP version 4 is the current standard deployed all across the world today.
Look, if you take just one technical specification away from this explainer today, it really should be this number right here, 179. BGP relies on TCP port 179 for the reliable transfer of all its packets. It doesn't rely on guesswork, right? It uses strict, reliable TCP handshakes to make sure routing updates are delivered precisely and securely. Pretty much every network engineer eventually gets this port number permanently burned into their memory.
There's a really fascinating myth out there about BGP. A lot of people just assume BGP is absolutely necessary anytime you need multiple connections to the internet for redundancy. But actually, fault tolerance for outbound traffic, that can be handled pretty easily by an interior protocol like OSPF. BGP's true superpower is in controlling how traffic enters the local AS. When you have multiple connections to external networks through different providers, BGP is what allows administrators to enforce strict routing policies on all that inbound traffic. It's a total game changer.
Section 2. IBGP versus eBGP peers. Neighbor relationships. For BGP to even function, routers have to form neighbor relationships, and there are two distinct ways they go about this.
Now, what's really interesting to see here is the stark contrast in the rules. Internal BGP, or IBGP, connects neighbors within the exact same autonomous system, which requires a full mesh connection. They carry an administrative distance, or AD, of 200. On the flip side, external BGP, or eBGP, bridges entirely separate systems. It's strictly assumed to be exactly one hop away, and it gets a highly trusted administrative distance of 20. And as we know, a lower distance means higher routing trust.
So think about how eBGP bridges the gap right across the boundary lines of different autonomous systems, while IBGP relationships happen entirely inside a single AS, relying on the underlying interior protocol of that network to stay connected. And remember, a Cisco router running BGP can only belong to one AS, and the operating system will only allow one BGP process to run on it at a time. No exceptions.
Moving on to Section 3, Building BGP Relationships, BGP State Machine. How do these routers actually talk to each other to share the world's routing tables? Well, they don't just magically connect. They follow a highly structured communication process.
BGP uses 4 distinct message types to do this over that TCP port 179. First, an open message is sent to initiate the session, exchanging things like the BGP version and router ID. Once connected, keep alive messages pulse back and forth every 60 seconds by default, just to make sure the neighbor hasn't gone completely offline. If 180 seconds pass without a keep alive, the peer is declared dead. Then we have update messages, which actually exchange the vital routing data. And finally, notification messages, which are basically the alarm bells. If a notification is sent, it means a fatal error occurred and the session is immediately torn down.
Let's move through this chronologically and see how it builds practically through the BGP finite state machine, which is this elegant 6-step handshake. It kicks off at idle, then it moves to connect while it waits for a TCP connection. If that fails, it drops into an active state, attempting to retry. But if the TCP connection succeeds, it bumps to open sent, firing off that initial open message. Next it hits open confirm, waiting for a keep alive in reply. And finally, it reaches the holy grail, established. This is the fully formed state where those update messages containing routing information can finally flow freely.
Section 4. The BGP Synchronization Rule, Avoiding Black Holes. Now we have to look at a historically tricky hurdle that network engineers have navigated for years to prevent a very specific, catastrophic kind of packet drop.
Imagine an autonomous system that serves as a transit bridge between two other distinct networks. A router on the edge receives an external BGP route update and quickly passes it to an internal BGP peer on the far side. That second router tries to send traffic to the new destination. But here's the catch. The routers sitting right in the middle of that transit network, which are just running a standard interior protocol, haven't learned the new route yet. When the traffic hits them, they literally have no idea where to send it. They just drop the packets. This is what we call the dreaded routing black hole.
So to fix this black hole issue, the BGP synchronization rule was born. It states that all routers in a transit AS must learn of a route through the interior gateway protocol first before BGP is allowed to advertise it to an external peer. It essentially forces the edge routers to sit and wait. Now, what's kind of funny about this is that modern interior networks are so fast, and full mesh IBGP is so incredibly common that the strict waiting period is largely unnecessary today. In fact, as of Cisco iOS version 12.28t, this synchronization rule is actually disabled by default.
Section 5. Scaling BGP Networks. Managing Limitations. As we learned earlier, internal BGP requires a full mesh connection, meaning every router peers with absolutely every other router. But as a network grows, that requirement quickly becomes a massive problem.
The formula for a full mesh means that if you add even just a few routers, the number of required connections skyrockets exponentially. This massive spiderweb of every router to every router connections drains incredible amounts of bandwidth and router CPU power. For giant internet service providers, maintaining a pure full mesh is simply unsustainable. I mean, it would mathematically collapse right under its own weight.
So to save the network, Cisco provides two brilliant engineering workarounds. The recommended method is route reflectors. Instead of a full mesh, client routers only peer with a central route reflector server. The server acts kind of like a hub, bouncing BGP updates to all clients, which massively reduces the number of connections you need. Alternatively, you have confederations. This approach takes a massive parent autonomous system and intentionally fractures it into smaller, more manageable sub-ASs. The routers inside the sub-AS act internally but form eBGP-like connections to the other sub-AS. Both strategies elegantly solve that massive scaling bottleneck. Well, we've seen how BGP routes traffic, how it builds complex state-machine relationships, and how it scales to handle truly massive networks. But it leaves us with kind of a provocative final thought. Without BGP, the global internet instantly splinters into millions of isolated islands, totally unable to communicate. If this single protocol is the only thing weaving our entire digital world together, just how fragile is this foundation? Like, what happens when these routers are lied to? That is a fascinating question and honestly, the perfect jumping off point for exploring network security next time. Thank you so much for learning with us today.